let's get started. So let me get the lights and whatnot adjusted. Okay, so I'm going to go ahead and get the sign-in sheet passed around so I don't forget. Let's talk a little bit about what we're, announcements of what we're talking about today. So again, if you haven't bought the steel manual yet, you really need to be doing that as soon as possible. And you all, of course, have the coupon code. I did want to mention again the technical conference. If you want your resume to be included in the booklet for all the practicing engineers and potential employers, you need to get it to Morgan 268 at Marshall by Tuesday. So if you're interested, I would be polishing it up and getting it ready. And also, if you're interested in volunteering for the day, contact Logan Stacks as soon as you can, because that will definitely help increase your chances for networking and things like that. Well, it's not going to increase your chances for networking. It's going to create them because you'll be there. Let's see. So today I'm going to assign homework 1. Now, just so everybody's aware, I'm assigning homework 1 in concrete as well. The one in here is due on Friday, and the one in concrete will be due the following Monday. So you won't have 2 assignments due on the same day. And honestly, this assignment's pretty short. It's not terribly difficult. I'd argue that the assignment in concrete design has a little more oomph to it, a little more meat to it. So spice. So I'm giving you more time on the concrete design homework than I am on this one. But this one's only 2 problems and it's pretty short. Sound good? Okay, so we're not just continuing our discussion on lateral loads, hopefully we're ending our discussion on lateral loads so that we can actually start getting into some stuff related to design. Now, I figured I would start here just to make sure everybody's on the same page. So last time we began our discussion of lateral loads, with some detail associated with it. And there's really only 2 lateral load effects that we need to assess: wind and seismic. So last time we went through wind, I think, in some pretty significant detail, or at least as much detail as we're going to go through in this course. So we discussed the base wind pressure equation and the factors that go along with it, exposure coefficients, topographic factors, directionality, and then, of course, our base wind speed. Of course, the one that's complicated is KZ. That's the one that you actually have to do a little bit of calculation for. We talked about risk categories. Risk categories affect seismic design as well, although we are going to kind of soften it a little bit. Just like wind, designing for earthquakes is going to be dependent on the type of structure that you're designing. I mean, you're going to approach seismic design differently for a 911 call center than you would for, say, a barn or a grain silo or something, because it's all about risks. There's more potential danger with the failure of a 911 call center than there would be for some barn or something. Now, KZ, like I said, that's the complicated one. That's the one we went through last time. I say it's complicated, but it really is pretty plug and chug. You just go through and calculate it out, just depending on the height of your structure. And the idea is if you have a really, really short structure that's less than 15 feet tall, we can just keep it simple and assume a constant wind pressure. For anything over 15 feet tall, that's where we need to start to assess wind speed or varying wind pressures as a function of building height. And these equations are valid up until Z sub G, this gradient height. And that's dependent upon the exposure category. But keep in mind that is pretty tall. I mean, category B, that model would be valid up until a height of 1,200 feet. It's a pretty tall building. All right. Does this sound good? Any questions? Yes? That's when you start breaking out. That's a good question. So what do you do if you're in excess of this? That's when you start doing things that are a whole heck of a lot more refined. I mean, it wouldn't be off the wall to do something like a wind tunnel test. Build a scale model of the structure and actually put it in a wind tunnel and start recording the response. That's pretty common for your really complicated structures. That's one way of going about it. And another way is to do some more refined, computer modeling and things like that. Sound good? Okay. So we went and did a pretty basic example to try and assess how you would compute base wind pressures at varying heights of the building. What you would then do with those pressures is similar to what we did in concrete design, regardless if you had it last year or 2 days ago, is we would take that wind pressure and then distribute it across the element's tributary area to determine, well, what's the point load I need to put on my RISA model or what have you. And we're going to do something somewhat similar today with seismic. Okay. Last thing I did want to mention, we're not doing everything associated with wind in here. There are some other issues, things like handling gusts and internal positive and negative pressures in a building under wind. I mean, we talked about last time, if you're in a building and it's really windy outside, I'm sure some of you have experienced that event where you open the door and the door has a tendency to either want to slam shut or stay open, like it literally sits there and stays open under heavy wind. That's because you can generate positive and negative internal pressures inside of a building. And sometimes you need to take that into account when you assess the frame. Yes, sir. Yeah.
We found the point loads for each story.
Mm-hmm.
Where in the story should we put the point loads?
All right, that's a good question. And typically, what's done is, okay, so here's the beam, and here's the beam, and here's the column. And usually, when you're like running a RISA analysis, you would just put it right here. We're going to come up with something very similar for seismic loads as well. And I think you'll see the analogy here in a little bit. Sound good? That's a good question, though, and we'll bring that up here in a little bit. Sound good? Okay. So, like I said, a couple other things. Again, the internal positive and negative pressures. Also, eccentricity. More often than not, we engineers would like to deal with buildings that are nice and rectangular and symmetric and easy to analyze. But what if we have a building that's something, like an L shape and, we have a wind attack it? Well, not only is that wind going to be applied to the frame, but it's probably going to want to take the building and twist it a little bit. So it's not very complicated to assess. I mean, we can talk about it later on when we go through some of our assignments. But the long and short of it is when you have a frame like that, usually you're going to take your wind and offset it some amount. So you'll have, let's say like a larger wind pressure on this side of the building than you would on this side to account for accidental eccentricity and things like that. If you can handle base wind pressure, then it's really just more provisions and pretty straightforward stuff. Sound good? All right. Let's talk a little bit about seismic. Let's try and get through that today. So like wind, seismic is a fairly significant lateral event that we have to assess for building structures. It's pretty straightforward if you understand the procedure. The long and short of it is this. It goes back to the basic analogy of if you're sitting in a car seat and you're driving down the road and the driver hits the brakes, you fling forward, okay? You fling forward because your body, i.e., like where your hips are, they don't have the lateral stability to hold you back during that sudden change in acceleration, and you fling forward. Now, to arrest that motion, we place a system inside the car to hold you back. We call that system a seat belt. So that seat belt experiences a force applied to it. And you would calculate that force by saying your body's mass undergoing a given acceleration. Force equals mass times acceleration, right? Same thing's true in a building. Now, the step-by-step process is it's a little more involved, but in the end, it is fairly plug and chug. So the first thing that you would do is determine the seismic response spectrum. And we're actually going to do that today, but it's pretty simple. It's all about just determining, based on your soil conditions and where you're at in the United States, you're going to have a different set of acceleration characteristics. I mean, we'd have different characteristics here in Huntington than we would in, say, Los Angeles or somewhere like that. The next thing we have to do is determine the building's period of vibration, and we'll talk about what that means later, but it's a fairly plug-and-chug expression. Based on that, we would determine the seismic response coefficient, and this is basically just how many Gs the building is that we should be designing the building for during an earthquake. So you've probably heard the expression, under acceleration, like fighter pilots, like they're hitting so many Gs. Like I'm sure you've heard that expression before. Well, if I were to take a building and literally pick it up and go like that and have the building be subjected to its own self-weight laterally, that would be the building being subjected to 1G, just gravity, okay? Well, under an earthquake, dependent upon where you're at, I mean, around here, we might not be subjected to 4 or 5 Gs. It's West Virginia. We really don't have significant acceleration issues around here, but we could if we were out somewhere like, say, California or somewhere like that. Once we determine how many Gs the building is responsible for, basically all we do is we take that total base shear and just say, all right, how much goes on this story, how much goes on this story, how much goes on this story, etc. And it's a pretty plug and chug expression. We talked about this last time, so I really don't want to illustrate it. This is just another one of those maps that highlights different effects across the country. For this one, we're looking at earthquake hazard levels. Depending upon where you're at, sometimes this can be kind of tough to determine. That's why we're going to use one of the a similar online design tool to help determine our accelerations. So what I want to do is look at determining the seismic response spectrum for a typical building here in Huntington. So just like last time, we're going to look up latitude and longitude for this region, and then we'll use this to help determine our response spectrum. Now, our response spectrum is going to look something like this. Basically, the idea is this. So this response spectrum is defined based on a given set of points, like design spectral accelerations at short periods and at long periods, and et cetera. I don't want to get too much into earthquake engineering, but the long and short of it is this. This will tell us, in a nutshell, how many Gs we should be designing the building for as a function of the building's period of vibration. So once we determine this, we can determine the period of vibration, and then that'll tell us how many Gs we have to design the building for, in a nutshell. Okay? Now, for this calculation, we're going to assume risk category 2, and we're going to assume that stiff soil is found at the site. And you'll see what that means here in a second. Now, all right, so everybody good so far? Okay. Now, the nice thing about this is there's a nice online tool that we can use. This is at USGS's website. Ooh, I don't want to use Internet Explorer. We're going to copy that and put it into Chrome. Oh, there it is. Let me go down a little bit. There we go. Okay. So Chrome's taking its time. All right. So this is a tool that will tell us the ground accelerations that we need to be using for design, depending upon where we're at in the United States. So the first thing we have to do is select the document we're going to use. So are we going to be using NEHRP? Are we going to be using the International Building Code? For us, we're going to be using ASCE 7. Remember, that's the document we're going to use to obtain our loads. So if you look here for this document, see how right here where it says 2010 ASCE 7? That's the one we're going to go off of. Okay. Now, report title, I don't know, we can call this example, what is it, 1B? Is that what we're on? Okay. All right, 1B. Okay. Site soil classification. So depending upon the soil characteristics that you have at your site, you're going to have different ground that the building is ultimately going to be responsible for. The default value would be site class D, which is pretty typical soil conditions for your site. But this is where the geotech engineer would come in and say, okay, here's the soil conditions you need to use for design. We'll go ahead and use site class D. Now we need to do a risk category. So pop quiz, if I've got a commercial office building, what risk category should I be using? 2. There we go. All right, so we have 2 choices, either anywhere between 1, 2, and 3, or risk category 4, so we'll use this one. Now, we need latitude and longitude, so I need to go back. I can go to something like Google, and I can say Huntington, West Virginia, latitude and longitude, and then there we go. Anybody remember what we have to do with these values? Anything particular we have to do? West has got to be negative, yeah. Okay, so there we go. So I'll copy, paste that. Copy, paste that. Okay. And then we'll compute values. See, now once I put the values in, it's sort of refreshed in there. You can see we're in the right spot because that's Huntington. So let me compute the values. When you use this tool, there you go, right there. The report shows up as a pop-up, so make sure you're allowing pop-ups. Hit done. Close that. Let me try it again. There we go. All right. So here's our summary. So it's showing a map of the location, so it's determining ground accelerations based on this point. So there you go. And so if you're wondering what these particular values mean or what they're going, so S sub S and S sub 1, this is the stuff that the geologists and the seismologists would report directly. These are the ground accelerations that are actually being measured at this particular site. So S sub S and the S sub 1 stands for essentially accelerations under short periods of vibration and accelerations under long periods of vibration. A long period is defined as 1 second. So short period of vibration would be like, long period would be, a little bit more exaggerated. Ooh, yeah. So, boom and boom, right? Like the sound effects? Now, the MS and the M1, those are the accelerations that have been modified based on the soil conditions that we provided. So we would get different modifications for site class B than we would for E, et cetera. And the DS and the D1 are the design accelerations. Those are the ones that we would actually use for design. Nice thing is that a lot of this is procedurally generated for us, and we really don't have to worry about it. If you want, you can view a detailed report, and it goes a little bit more into, based on this soil condition, this is the value that we looked up from this table, et cetera, et cetera. This is a really nifty tool. I think just about any structural engineer that's designing in earthquake zones uses this quite a bit. But all in all, really what we're interested in from a design aspect is really this. So from a design standpoint, this building would be subject to about 16 Gs or 0.11 Gs or 0.12 Gs, I guess I should say, depending upon the building's period of vibration. Which, I mean, we're in Huntington, West Virginia. We're not in LA. See what I mean? Let's play around with this. Let's see what would happen if we were in LA. Let's just try that out. So. California. You don't want to hear me sing. You really don't. Okay. All right. So look right here. A lot different, right? So we're looking at 1.6 Gs or 0.85 Gs. Well, it's because it's Los Angeles. That's earthquake zone. Yes, sir. Because that's a good question. There's a difference between what accelerations you're actually seeing on the ground versus how much of that acceleration is actually being transferred to the building. And you can actually calculate this really easily. That's a really tough judgment to make for every single building everywhere in the United States under every condition. So this is one of those things where they just used a rule of thumb and went with it. And the rule of thumb is about 2/3. So if you take these values and multiply them by 2/3, you'll get that. That's a good question. So
how huge of a change from a design standpoint would it be between what this design specification is saying and what?
Oh, quite a bit.
So like that makes a real big change.
Oh, absolutely. Without getting too much into the world of earthquake engineering, when you start getting into these high seismic zones, you have to sort of completely rethink your seismic system altogether. There are companies out there that all they do is make different types of bracing that's only purpose is meant to be used in high seismic zones. So like around here, we would use something pretty simple, like some base, some steel tubing or some T-shapes or some I-beams or something like that, and that's it. Because we're not in earthquake zones. Out there, that's not good enough. They're having to use special bracing systems solely for those types of events. And in the world of earthquake engineering, I mean, that's crazy. That's a crazy amount of force. usually in those instances, there's no way that you can design the building completely to resist those types of loads. In other words, you're going to get some elements that fail during a large earthquake. There's no avoiding it. It's all about which elements fail and you as the engineer detailing your structure so that certain elements fail first. Here's a good analogy. So why do we put a fuse box in a house? Why do we have a breaker box? No, continue that thought. Continue that thought.
Pretty much it's blowing stuff up because if something goes wrong, we can just plug fuse in there.
What happens when, what would happen?
Yeah.
A fire. So we place a fuse box or a breaker box in a building so that it trips before we cause a fire, right? Now let me restate that from a structural engineering aspect. When we design a building, we're actually selecting elements and we're saying the purpose of that element is to fail before the whole structure does. Makes sense? That's a weird thing to think about as a structural engineer, that you're actually selecting particular elements to fail, but it's exactly what you're doing. We call them structural fuses. A very common structural fuse in the world of steel design is to use what's called a reduced beam section. The idea is if you've got a frame and you've got beams and columns, which would you want to fail first, the beams or the columns? And the answer is the beams, because if the columns fail, that's the whole building. If the beams fail, well, it sucks, but it's just that one element, okay? So actually to force failure in the beams, to make sure that the beams fail before the columns do, we actually take the beam and cut out a small piece of the beam. Like we create a weak spot in the beam so that when the earthquake happens, all the failure gets concentrated right there. We actually do something quite similar in vehicles. You know, I mean, you've seen what a car looks like after a car crash. It's a mess. But the idea is that we create these weak spots in the frame of the car so that under a car crash, they absorb all that kinetic energy and they fail instead of that kinetic energy getting transferred to you and you dying instantly. Make sense? So that philosophy is sort of used across the board. But this is good stuff. I just wanted to go through some of this stuff with you. Anybody got any questions?
So that's used in seismic design and not just like regular.
Yeah, you wouldn't do that here, but you would do that in high seismic zones. Absolutely, yes. Again, the philosophy behind earthquake engineering is a little different than in just regular, run-of-the-mill design. Because in earthquake engineering, we know that under large earthquake events, we're going to have failures. There's no way around it. So we just want to make sure that the whole building doesn't fall down and that people can escape. I mean, let's put it like this. If I was a structural engineer and I was designing a commercial office building in LA and a large earthquake hit and the entire structure failed, I would be just fine with that as long as nobody died. You see what I mean? So, and that's sort of the general impetus behind earthquake engineering. Yes, sir.
So the structure in LA, losing earthquake and 3-4 elements fail, but the whole structure still fine. Now, what's next? What to do with the structure?
Now it's time to call the insurance companies and get your structure rebuilt. but I mean that's why you have insurance. Yes, sir.
I mean, how would that work there with like engineering law? Design a building that failed, you're responsible. People die, but people responsible.
Well, but I mean, is to design the structures so that it doesn't kill people. That's the whole point. Think about it like this. Okay, you could design an electrical system in a building that under ideal conditions could accept the currents and the voltages that were being subjected to it, but you'd still put a fuse box in the building, right? You see what I mean? Is somebody going to, think about it like this, is somebody going to sue the electrical engineer if the fuse panel trips? No, because it's performing as it was intended. That element failed so that the house didn't burn down. It's the same idea in a structural engineering system. We'll force failure in that particular element so that the people can escape and people won't die. Okay? Does that make sense? In that instance, the building's actually performing exactly as intended. Okay? I mean, you also have to keep in mind, I mean, we're talking about massive amounts of force under earthquake events. We're going to have failures. There's no way to avoid it. You see what I mean? Everybody else okay with that? These are good questions, and I really want to explore this stuff just to make sure everybody's understanding it. Sound good? Okay. So is everybody okay with those seismic characteristics, like those ground accelerations? Everybody okay with that? Now, what you ultimately generate when you go through that is something like this image over here on the right. And basically, this is telling you how many G's the building is responsible for. In a nutshell, this is how many G's the building is responsible for as a function of the building's period. So what is the building's period? Well, one of the fundamental principles of not just structural engineering, but this is really just more physics in general, is that under free vibration, any structure will vibrate according to what's called natural frequency. This is one of the reasons why a lot of musical instruments like guitars or pianos or things like that tend to work. I mean, we can think about a guitar or a piano, it'll work the same way. I mean, imagine if I have, a classical piano right in front of me, not an electric one, but the ones with the strings in the back, okay? Now, let's say I take a particular key and I do one of two things. I take the key and I play it really lightly, or I take that key and I mash on it, okay? Now, what's going to happen, what's the difference between playing the key really lightly and hitting it, really hard? I get a louder sound, right? But does the note change, or is it still a C sharp, right? It's still the same note, okay? What happens in the piano is that once you hit that string and that hammer strikes the string, after that, the string is vibrating on its own. It's going boom, right? And it's vibrating on its own. It's vibrating according to a certain frequency. It's natural frequency. So many cycles of vibration per second, so many hertz. Doesn't matter if I hit the string very softly or with a lot of force. In the end, it's the same frequency. Well, the same thing is true in guitars or anything like that. The same thing is true as well in buildings. Okay, what are you doing in an earthquake? You're taking the building and you're subjecting it to a large amount of acceleration. So under those vibration events, the building is going to want to vibrate. Make sense? Okay. Now, there's a whole school of structural engineering called structural dynamics. The whole point of that science is to try and determine what is the building's period of vibration, and what is any structure's period of vibration, what's a beam's period of vibration, what's a column's period of vibration, what is a frame's period of vibration, et cetera, et cetera. It is not an easy thing to compute. There's a lot of diffie-Q, a lot of math, a lot of matrix analysis, all geared around that particular science. Luckily for the regular old design engineer, there are some very basic models that we can use to compute what's called the building's period. The building's period is just how long it takes for the building to go through a given cycle. So if here's the building, it vibrates and comes back. However long that cycle of vibration takes, that's the building's period of vibration. Sound reasonable? Okay. So there's a very nice plug and chug expression that we can use, and this just comes from doing a lot of analysis and a lot of data assessment on brace frames, moment frames, et cetera. So this is a formula for the approximate period of vibration, so T sub A, and it's basically a function of the height of the building, H sub n, that's how tall the building is, and two constants, C sub T and X. And they depend on the type of building that you're looking at. In other words, a brace frame is going to behave a little differently than a moment frame. Make sense? Okay. So this is a table directly out of ASCE 7. You can see there's steel, concrete, or steel moment resisting frames, concrete moment resisting frames, all sorts of stuff. What I decided to do, I just blew up the values that are going to be important for us. So brace frames and moment frames. All right. Sound good? Okay. Now, once you determine the building's period of vibration and you've got that seismic response spectra, you can then determine how many G's the building is responsible for, and that's this constant C sub S. I'm soft pedaling this a little bit, I'll be perfectly honest, because there's a little bit of math that goes into C sub S, but primarily it's a function of that response spectrum that we looked up earlier using that USGS website. It's going to be a function, obviously, of the building's period and where it's at. It's going to be a function of the building's risk category, whether or not it's risk category 3 or 4 or what have you. But the one I'm soft pedaling a little bit because I don't want to inundate you with too many details is how much yielding is tolerated. You know, depending upon where the structure is, like I said, sometimes we can hit some really crazy G's, right? I remember how I was saying there's all sorts of unique systems that sole purpose is, you know, to fail during earthquakes. Well, depending upon the different type of system that you're using, you have different response characteristics that you would use to determine C sub S. So I am soft pedaling that a little bit, but I just wanted to give you a general understanding of where that comes from. Ultimately, what I'm interested in is that given a C sub S value, you could then take the weight of that building and determine how much force needs to be applied to each story. And I know the equation looks really complicated. It's actually really simple. This is just a distribution factor that'll tell you, okay, based on that base shear, compute, or, you know, put 20% on this story, or 30% on this story, or 15% on that story, and that's basically it. Don't worry, we're going to go through a really basic example on how to do this, and I think you'll see it's pretty straightforward. So the only thing I think that's worth mentioning is this distribution coefficient. If your period of your building is less than 1 second, we take this value to equal 1. If it's larger than 2.5 seconds, we take it to equal 2. And anywhere in between, we would use linear interpolation, and that's basically it. If the details are a little fuzzy, don't worry. I think this one will clear it up quite a lot. So this is the same building that we've been looking at. Now, real quick, is this you tell me, this looks like a brace frame or a moment frame? Moment frame. There's no braces in it, right? So here's the moment frame. Now, what I've done on this example that wasn't on previous slides is if you look, I've got the weights of each story. So imagine, you know, if we were looking at this building, let's say this is the second story, I'm computing the weight of the entire story, you know, the slab, the drop ceiling, the electrical, everywhere along that story. So for this building, we'll say that the second story weighs 250 kips. This third story weighs 300 kips, etc. All right, sound good?
So,
yes.
When we calculate the weight of the floor, so for the 250 kips, that's assuming whatever is sitting on the floor, the second story, and whatever is hanging from the roof?
No. This would just be the weight of the roof system. This would just be the weight of the fourth story, the third story, and the second story. Now, we're ultimately going to need the total weight of the building, but we're just taking it story by story. That's a good question. Everybody okay with that? Sound good? All right. That and the geometry of the building. I mean, think the weight of the second story here is going to be different than the weight of the second story over in Smith, right?
Yeah.
It's a different building altogether. Yeah.
Just kind of like you said yesterday or the day before, like if you're building a library.
Exactly. I mean, if you look at the floor system over in Drinko, that sucker is stout. It's not going anywhere. So, but that's actually a concrete design topic, and we'll talk about that later. All right. Sound good? All right. The long and short of it for this example is that to keep things a little simple, I'm going to give you the seismic design coefficient, and we're going to take that to equal 0.1. All right. Sound good? All right. Let's do some calcs. Let's see if we can go through this. So, all right. Now, help me out with something. So we'll say example 1C. What's the total weight? Somebody said, I heard 700 and 800. 800, all right. 800 kips. Okay, all right. So to give you kind of an idea of what we're doing, here's the long and short of it. So, okay. So the total weight of the building is 800 kips. Now, our seismic response coefficient C sub S is 0.1. So that's more realistic. Yeah, that's more expected of what we would get around here. All right. So this is 0.1. So what this means is that the total base shear V is 0.1 times 800 kips, which is 80 kips. So if you're wondering what total base shear is, basically that's just saying under an earthquake, that's how much lateral force the whole building is being subjected to. What we need to determine is how much of that force needs to go to each story. Okay? Sound good? All right. Okay. Now, over here on the side, we're dealing with a moment frame. Bless you. Oh, frame. Okay. So help me out with this, this moment frame. Let's see. If it's a moment frame, answer me two things. What is C sub t and what is x? Say it again. 0.028. And x is, all right. Now, h sub n is the total height of the building from the ground. So how tall is the building, essentially? 53 feet? Anybody else getting that? Okay, all right. What that tells us is we can determine the approximate period of the building. So that's CT HN to the x, which is 0.028, 53 feet raised to the 0.8. Now I know the units are going to be a little crazy. Ultimately, whatever answer we get is going to be in seconds. You should get a fairly low value. $18.84. Is that raised to the 0.8? Huh. Yeah, yeah. That's what I'm getting. 0.67. Is it 0.671? You getting it? Is that? Is it 0.0? Yeah, yeah. That's what I'm getting. Yeah. Oh. I see where you're getting. Hold on. Let's try this. What's this? Oh. I'm sorry. Hold on. I'm sorry. Is that better? Got any other comments about my handwriting? Is that what it is? I'm kidding. All right. Now, so what this is telling us is for this particular building, okay, if I subject it to an earthquake, under free vibration, it's going to undergo a full cycle of deformation in about 0.67 seconds. So here's the building, under free vibration, it's going to go like that and like that. And that action is going to take about 0.67 seconds. So, it's like, woo, woo. Because you have to bring it back. Yeah. Now, where we use this value, actually I know it might seem a little insignificant, but we use this value to determine K. And what is K going to be if this is our building period? You'll find that in that distribution table. 1. So let me pull that up just to make sure everybody's clear about that. So here's our distribution methodology, and our distribution coefficient, how much force we distribute to each floor, is a function of that building period. So we have a building period that's less than 1 second, so we'll just take it to equal 1. Does that sound good? Everybody okay with that? Okay. Now, using this formula, I know it looks funky, but it's actually really simple. And the easiest way to go about it is to set this up in a table. Okay? So I'm going to set this up down here. And don't worry, I posted an Excel sheet that goes through a lot of this, so if you've got any issues, I think you'll find it's pretty straightforward. So, okay. Okay. So the first thing that we're going to do is list the stories of the building, and I think it's easiest to actually go based off the image on the slide. So literally put the roof first, and then the 4th story, the 3rd story, and the 2nd story. I think that's the easiest, because that way you can literally just read the weights. Okay. Now, help me out with this. So the first thing we're going to list is W sub X. Now, what that is just the weight of each story. Okay? So what's the weight of the roof, the 4th floor, the 3rd floor, and the 2nd floor? 250. Simple, right? Now, the next thing we're going to list is H sub X. And that's just the height of each story. So if you want, you could, it might be easier to actually start at the bottom. So how far is it from the ground to the 2nd story? 12. How far is it from the ground to the 3rd story? No. From there you go. There you go, yeah. 26. So the next one is 41. And then the last one is 53. That's a check because that's how tall the building is, right? So this is where being careful in your documentation can matter. Now, what I'm going to compute is this. I'm going to compute WH raised to the K, okay? So it's just the H raised to the K, and then multiply that times W. But the nice thing is K is 1. So anything raised to the first is itself. So all in all we're going to do is, what's 50 times 53? There we go. What is the next one? That's going to be what? 8,200? Next one's going to be something about like, what, 7,800? And then 3,000. Now, before we go on, I want to sum up that column. So somebody sum that column up. Tell me what you get. All right. Everybody else get that? Okay. Now, see this formula here? Now I'll show you why we did this. All right. See this formula? This formula is a distribution coefficient, and it basically tells us how much of that base shear goes to each story. So the way that we do that is we take this WH raised to the K for a given story and divide it by the sum of them for all the stories. So it's actually pretty basic. So to determine, I'll pull that up here in a second. So to determine the first one, so we'll put in a column for CVX, not the pharmacy. CVS, I know, that's what I'm saying, CVX. So to determine the first one, all we would do is take 2650 and divide it by the sum of all this, which is this. So what's 2650 divided by that? 0.122. And the next one is, there we go. And then the next two I'll go ahead and tell you are 0.36 and 0.139. Sound good? The only thing you have to do is to determine the force is to just take CVX times V. So in other words, what is the base shear that the entire building is responsible for? Anybody remember? It's on the screen. 80, right? So this much of 80, this much of 80, this much of 80, and this much of 80 goes to each story, and that's it. Yes, sir?
Is this like a fancy weighted average?
Basically, that's all it is. It's a fancy weighted average. So if I take 0.122 times 80, that should be 9.79. 30.3, 28 point, here let me put another decimal there, 0.82, and 11.09. And you can check your math by summing all those up, and you'll find that they add up to be 80. You believe me? I appreciate that. All right. Any questions? So that you understand the meaning of what these values are, literally what I would do is I would, break out the RISA analysis, and I would say, okay, here's my frame. I would go in and put the joints and the boundary conditions, and then I would just say, okay, up here, put 9.79. Here, put 30.3, and et cetera. And then there you go. That would be my seismic analysis. All right? Sound good? Any questions?
Does directionality matter?
Direction.
With
No, because that's a good question. And no, because it can go either way.
But that assuming that you're building symmetrical.
Well, you're also getting, those are other issues as well. It's similar to what was going on with wind. Under an earthquake, the building might not just want to go this way; it might want to rotate, just because its profile, just because of its plane profile. And this is kind of what you were mentioning after class earlier. You had also mentioned the Taipei 101. Basically, that big tuned mass damper. It's just a big mass that's trying to keep it centered during an earthquake. So yeah. All right. Everybody good? Okay. I'm going to go through this really quickly because if you've had concrete design already, you've seen this stuff before, and if you haven't, we're going to talk about this here in about 10 minutes. But I did want to at least very briefly mention some of the stuff that you folks who haven't had concrete design in a while might want to see. So first off, dead loads. I think everybody who's had concrete design ought to remember that. Remember, it's basically the self-weight. Remember, the two unit weights I want drilled into your head are the unit weight of steel and the unit weight of reinforced concrete. I know my folks who've already had concrete design know that's burned into your memory by now. Anything else you can look up? You all remember that, don't you? Yeah, I know you do. We're going to talk about this in concrete design next time, but live loads also are dependent on the type of structure you're assessing, whether or not you're looking at a library or a school or an office building. You have different live loads, but I know my concrete folks also remember live load reduction, right? So I'll soft pedal that for now because we're going to talk about that in very significant detail later. But the question is, do you have to design for the entire maximum live load in most cases? And the answer is no. And that's where live load reduction comes into play. And I know my concrete folks remember that. Lastly, snow. We didn't use that in very significant detail in concrete design before, and we're really not going to do that as well this year. We'll just sort of discuss that in the next class. The long and short of it, though, is snow loads are a function of where you're at. And that's basically it in terms of loads for steel design. For concrete design, we'll talk about some of this stuff here in a little bit. Sound good? All right. I've got a at-home assignment for you, a present. It is due on Friday. The concrete design homework will be due the following Monday, so you've got some time on it. So, homework? Yeah, I'm going to stop the recording and I'm going to hand it out. And then we're done. Sound good? All right.